Hello and welcome to today's session. In today's session, I am going to make you familiar with the concept of reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with an environment. Unlike supervised learning, where the model learns from a labeled dataset, reinforcement learning is based on a pun, is based on a reward punishment mechanism that encourages the agent to learn from its own actions to maximize cumulative reward. Here's a breakdown of RL concepts. Core components: first is agent, the learner or decision maker; second is environment, the setting or world the agent interacts with; third is action, the choices the agent can make; fourth is state, the current situation or observation of the environment; fifth is reward, the feedback that agent receives from the environment after taking an action. Positive rewards reinforce good actions and negative ones discourage bad actions. Types of reinforcement learning. Model free: the agent learns a policy directly from the environment without any knowledge of the underlying model. Common algorithms include q-learning and SARSA. Model based: the agent builds a model of the environment's dynamics and uses this model to simulate outcomes, helping it make better decisions. Key concepts: policy, a strategy that the agent uses to decide actions based on the current state. Value function, estimates the expected long-term return for a state. Q value, estimates the expected return of taking an action in a given state and then following the policy. Exploration versus exploitation, balancing between exploring new actions to discover their potential rewards and exploiting known actions that yield high rewards. Learning algorithms. Learning algorithms. Q-learning, a model-free algorithm that learns a Q-value function. Q-learning, a model-free algorithm that learns a Q-value function where the agent updates its knowledge of action value pairs. Deep Q networks combines Q-learning with deep learning by using neural networks to approximate Q values from complex environments. Policy gradient methods directly optimize the policy by adjusting it to maximize the expected reward. Actor critic combines the advantages of policy gradient actor with value function methods critic to reduce variance and improve learning stability. Applications. Games. RL has achieved applications. Games. RL has achieved remarkable success in gaming such as AlphaGo and OpenAI's Dota 2 bot. Robotics. Agents learn to control robots for tasks like walking, grasping, and obstacle avoidance. Finance. Used for automated training. Finance. Used for automated training where the agent learns strategies that maximize returns. Healthcare. Used in treatment planning and optimizing resource allocations. So, now let me demonstrate a Python program in which I have implemented reinforcement learning. So this is the Python program in which I have implemented reinforcement learning. So firstly, let me execute this particular Python program in which I have implemented reinforcement learning. Now let me explain this Python program or let me break down this Python program in which I have implemented reinforcement learning. So first is grid and initialization. The grid is 4 into 4 or 4 by 4 and the agent starts at 0 0 with the goal at 3 3. The obstacles are located at 1 1 and 2 1. Queue table. A 3D queue table is initialized where each state xy has 4 possible actions: up, down, left, right. Each entry in the queue table stores the expected reward for taking an action from that state. Queue learning. The agent follows an epsilon greedy policy for action selection. With a probability epsilon, it explores a random action, otherwise it exploits the best known action based on the queue table. After each action, the Q value is updated using the following Bellman equation, where alpha is the learning rate, beta is the discount factor, R is the reward, S dash is the next state, and A dash is the next action. Training. The agent is trained over multiple episodes, 1000 in this case, gradually improving its policy based on past experiences. Testing. After training, the agent's path to the goal is tested, showing how well it has learned to navigate the grid. So, I am once again executing this particular Python program in which I have implemented reinforcement learning. So now let me explain the output. The training process will print the reward for each episode, and after training it will output the path the agent takes to reach the goal. The simple Q-learning example can be expanded or modified to handle more complex environments and actions. Challenges in reinforcement learning. Exploration. Striking the right balance between exploration and exploitation is challenging. Sample efficiency. RL often requires a large number of interactions, making it computationally expensive. Stability. Many reinforcement learning algorithms struggle with stability, especially in complex environments. So next is Q-learning. Q-learning is a popular reinforcement learning algorithm for finding the optimal action selection policy for an agent. It's a type of model-free off-policy learning algorithm, meaning the agent learns directly from experience without needing a model of the environment's dynamics. Here is a breakdown of Q-learning and how it works. Core idea of Q-learning. In Q-learning, the agent learns a Q-value function, which represents the expected cumulative reward of taking an action AAA in a state SSS and then following the best policy from that point onward. The Q value allows the agent to estimate the quality of each action in every state. The ultimate goal of Q learning is to learn the optimal Q values so that the agent can select actions that that maximize the cumulative reward. Advantages and disadvantages of Q learning. Advantages: simple and effective for discrete action spaces, learns optimal Q values without needing a model of the environment, model free, off policy so it doesn't require learning only from the optimal policy. Disadvantages of Q learning: not suitable for large or continuous state spaces without modification, example DQN for deep Q learning. Q values can be sensitive to the choice of learning rate and discount factor. Next point is Q learning applications. Q learning is widely used in problems where an agent must learn optimal policies such as game playing, example chess, tic-tac-toe, navigation tasks, example robot movement, inventory management in business, financial trading. So that's all for today. Thank you for listening me patiently. I hope everyone must have got an idea of reinforcement learning. Let's meet during the next session or during the next video.